I'm going to give you today's talk. Maybe just a question. Can you see the pointer? The mouse pointer? Okay.
Yes, we
so
can.
I can use it. The thing I'm going to speak is work that I have been doing with Justin de Keyser, who was a PhD student. He was a PhD student here at UC Louvain, and now he has switched first to insurance and then to data science. And so he's not anymore in academia, but we had a nice work we did together, and I wanted to present to you. So the question here, so there's a question about vortices. This is the topic of the workshop, and then there's what is called lake equations. And so the idea of lake equations. So first, I'm going to present to you what I mean by the lake model. And so behind the lake model, there are some. We start from a few assumptions. So the idea of the lake equations is to describe an incompressible and perfect flow. So this is just like the Euler equation. And you start from a three-dimensional situation, and but you consider something that is looking like a lake. And the point in the lake is that the level of the free surface does not change a lot. This is what's happening. So you have small variations of the level of the free surface of your lake. So essentially, your lake looks flat. And then the second thing is to say that the water in your lake does not move up and down. It moves essentially horizontally, or at least the vertical velocities are much smaller than what the horizontal velocities are doing. And so you can just consider that you have essentially a horizontal movement. And then the last thing is that you're assuming that the horizontal variations, they are occurring at a much larger scale than what the depth of your lake is. And so you're assuming that you're going to model some kind of large scale behavior on your lake. So this is the point in the assumptions. And then when you write the equations, you get something that really looks like the Euler equation. So if you look at this thing, you have essentially, so this is a two-dimensional domain. The two-dimensional domain is the domain of your lake. If you look at a map on a geographical map, this is what the shape that you will see. B is going to give you the depth. The depth is going to be a non-negative number. And when you're modeling it, when there is some fluid, it should be positive, and you should assume that it's going to zero when you have something like an island or a shore or something like that. And then you have v, which is a horizontal velocity, and these equations look like the Euler equation, except that you have some kind of density put in front of the incompressibility condition. So you're changing the incompressibility condition. Instead of having divergence of v being equal to zero, it's b times v, which is divergence free. So this is the point of the lake equation. And then you can see that the pressure, here I have named it h instead of p. And so the interpretation is that if you have a lake, I said that, so maybe first look at in the Euler equation, the pressure, this is some kind of an incompressible fluid. There should be, the pressure should be at the first order constant, and then you have the pressure that appears as some kind of multiplier in your equations, and which gives you some kind of second order, the second term in the expansion that you would have in your thermodynamical pressure. Here you have the same kind of phenomenon, but the pressure is, in fact, when you have a lake, this is the only thing that you can see really. What I mean by that is that what explains the role of the pressure is going to be related to the height, to the height of to the water level that you will have at everywhere. So I have said that there is some small variations, and those small variations of the water level, they will make some kind of ripples on the top of your lake, on the lake surface, and this small deformation at the surface, this is going to be the function h. So h is going to be it's going to describe the shape of the surface of your lake, in fact, if you observe your lake. And if you are just looking at your lake from a nice point of view, this is the only thing you're going to see. So this is about the interpretation, and then so we have this what I call the height deviation, which means that you have some small, you're not exactly at the level 0 everywhere you lake. You can be at a slightly higher or slightly lower level, and this is what you're going to see. And so about this lake equations. So the question we're having, maybe first before going on to the question, I just want to say that you have, as for the Euler equation, you can study if you put nice assumptions. If you're ready to put assumptions on B, you can go through. You can recover many elements of the standard theory for existence of solutions for the Euler equation. Things can become tricky if you begin having B, which can make some jumps, which can make some sense. You can have some kind of cliffs in the bottom of your lake. This can make sense physically, but it's more difficult mathematically. But you have a good theory of Cauchy problems for this equation, especially if you're staying in a class of smooth, nice initial vortices. This is the point about this model here. And so now the question is, can we say something about the motion of vortices? And so here, this picture, in fact, this is motivating the question that this is a vortex on the surface of a lake. There's another thing which is interesting, that you're really seeing the presence of this vortex because of this height function, this h function. This is going to give you the shape you're seeing here. And so the idea is to say, the question is, what is known about vortices for the Euler equation? And I first review standard results that already have been mentioned for the Euler equation. So if you take the Euler equation, you have some vortex dynamics. And so the question is, what can we get as vortex dynamics for the lake equation? And so let us first go to the two-dimensional, I will speak about two things, the two-dimensional and then the vortex strings for the Euler equations. And those are two problems which you can see, in fact, as I explained to you, these are kind of special cases of the lake equations with quite different features. So it's not, and so the first thing, so the Euler equation, I shouldn't say, so it's exactly, if you come from the lake equations, I would say this is the lake equations in which you have taken B to be equal to 1, and you have replaced H, the height, by the pressure. And this is a lake with constant depth. And what is going to happen here is that you have singular solutions which are obeying these equations of this kind of Hamiltonian system. And you will have a velocity given by this kind of singular, which is going to be behave like essentially 1 over the distance, and which is rotating around your vortex point here. And you have a pressure function given by this. Remember, I'm always mentioning this because this is the kind of structure you would expect to see on the surface of your lake here. And so this is the thing about the lake equation, the Euler equation, and maybe things that can happen. At first, you can just consider I just to take the value, just to have one vortex, and then you have just a stationary single vortex that sits in the middle of your Euclidean plane. You can have, for those kind of problems, translating pair of vortices, and then you can have complicated rotating systems of 3 vortices and lots of choreographies everywhere. This is not the point here, but there's a rich structure of solutions that can arise. And so, as a transition to the lake model, in the lake model, you have a shore on your lake. This is a problem which has a boundary. And so, if you want to look at the Euler equation in the domain, you can add a condition that the fluid does not flow through your boundary. And if you add this condition that the fluid does not flow through your boundary, then you can find you have different equations for your vortices. So let me explain to you what you're going to have. So you can still say that the position is going to be a solution here to a Hamiltonian system with some gradient of some function w, and I'm going to explain you immediately what this w is. This w, this is called the Kirchhoff root function, and this Kirchhoff root function, so this function there, this is going to be where does this Kirchhoff root function comes from? So you have, first you have the strength of your vortex divided by 2, which comes as a normalizing kind of factor. And this Kirchhoff root function is going to be the regular part of the green function. So the green function g, this is the solution of the problem. You're searching from Laplacian g is equal to Dirac delta, and you're imposing 0 boundary conditions on the boundary. And so note that there's a difference. You're taking somewhere an orthogonal gradient, so you're transforming some kind of information on a normal component to a fact that g would be constant here on the boundary. And then you can look at the limit of the regular part of the green function. This is going to be the difference between your green function and the green function, or a green function with a kind of standard choice of the green function on the Euclidean plane. And you're going to subtract this difference and look at the behavior of the limit. And so this will give you something which is some kind of the which will describe, in fact, what is happening, the kind of things that are happening when you're going close to a singularity. You know that when you're going close to a singularity, your green function is behaving like this singular term, and then you have this, when you're computing this limit, you're in fact looking what is happening at the next order, next to a singularity of your green function. And so the interesting thing here is that you have a kind of interaction with the boundary. So if you look at this green function, the symmetric part of the green function, it gives you some kind of phenomenon of repulsion with the boundary. And you can think in some cases, especially when you have the half, if you can think something like the half plane or a disk, in such case, you can, in fact, in the case of the half plane, in fact, you can think that the vortex moves as if there was a mirror vortex sitting at the symmetric point with respect to the boundary. This is what's happening with the half space when you have different shapes. It's not going to be as simple, but this gives you a good idea. You have some kind of interaction with the boundary, which is an interaction as if you were interacting with a vortex with opposite sign. So this is this Kirchhoff root function, and this says in particular, since you're moving in some kind parallelly to the boundary, this will give you something like parallel movement with respect to the boundary, not exactly, but something like. And this shows you that there is no possibility of your vortex to go and to collide with the boundary. And this is consistent with the Euler equations, which says that with this impermeability condition, your vorticity cannot get out of your domain. And if your vorticity cannot get out of your domain, this should also mean that if you're looking at the associated Hamiltonian system, your vortex point cannot go out of your domain. So if you believe in the connection, you should have this kind of repulsion phenomenon from the boundary, because there is no way of the vortex going through the boundary because there is no flux to the boundary. And about results, so I will speak about two different kinds of results. Is that if you consider a point, so there are results about stationary vortices. So the idea there is that if you have a point, say, going back there, if you have a point where the gradient of the Kirchhoff root function w is vanishing, then your vortex should stay at the same place. You should have a constant solution of this dynamical system. So you have an equilibrium point here, and so this should give you, there should be somewhere a vortex sitting there. And so there's this desingularization. The idea is to say that those, maybe just going back here, those, when you have those So you have these solutions. They have very. If you look at the velocity here, this is something which is not, say, it's not going to be even in L2 here. So it's not a solution in a very reasonable sense. And so the idea of the singularization is to say that stationary solutions of the Hamiltonian system, this is the stationary problem, stationary solutions of the Kirchhoff-Root system, they are limit of stationary solutions to the Euler equation. And so we have different kinds of results, constructions which can be based on different kind of variational principles. So there are what I call vorticity method. The idea is to construct first the vorticity, this is the curve of the velocity, as a solution of a maximization problem in the kinetic energy. And another approach is to go to take as a variable the stream function. So the stream function is a function such that the velocity is the orthogonal gradient to your stream function. And so for solutions of the Euler equation, the nice point is that if you know that you can write the vorticity as a function of the value of this, if the value of the vorticity can be obtained as a value, as a function of a value of the stream function, then you get automatically solutions. And so you have approaches concentrating on the vorticity, take the vorticity as an unknown in your problem, and you can also start out the stream functions, and you have different ways of getting solutions and studying the asymptotics and recovering the fact that you're obeying the equations here. Not exactly. What you get is that you can say that the vortex is stationary when the right-hand side is 0. You have a solution. You have a stationary solution to your Euler equation. So this is about the situation for stationary vortices. Now, still speaking about the Euler equation. So if we speak again about the Euler equation, you can, the real dream result is to be able to say that you can get a solution to the full evolution problem. And you can say that those singular solutions, they are limits of classical solutions for the evolution problem. And so this is the result of Marchioro and Pulvirente obtained in 1983. So this has been done in some kind, if you look at the dates on the previous slide, this is done in parallel. And what you have is that if you can say that the curl of your, so this is the vorticity of your, so the curl of your velocity, if it converges to a sum of Dirac deltas, so this is the initial condition, then if you look to the solutions of the evolution problem, when epsilon is going to 0, they believe as solution of the dynamical system. So this is the point, the result of Marchioro and Pulvirente. And so this is really a striking result, which says that the singular dynamics of the vortex of the dynamics of singular vortices, this is really the limiting behavior of solutions to the Euler equation. And so now I'm going to move to a different problem, which is the problem of vortex ring, which has also been mentioned, but I'm just going to, you see a very nice name here on the bottom right corner of this, on this bottom right quadrant of the slide here. So the idea is to consider the situation in which you have a fluid which has some cylindrical symmetry. So you're considering the situation of an axisymmetric solution, and you also consider that there is no swirl in your flow. This means that so you have an axis of symmetry, and what you can say about the velocity at every point is that it's a linear combination of something which is parallel to your axis and parallel to the normal passing from the point and going to your axis of symmetry. So you have naturally two directions, the direction of your axis and the direction given by, in fact, the flow is happening, and the better way to say this is that the velocity is in the plane containing the point you're considering and containing the axis of symmetry. So it's always contained in the plane connecting you to the axis of symmetry. And so the typical result about this, so you have, so maybe there's a long story between the first description of the possibility of vortices, then formulas for the velocity, then construction of one specific solution, which is a spherical vortex, to other results giving you solutions to the Euler equation. So what you have is that you have a vortex ring, which is a torus of major radius r and minor radius epsilon. The circulation around your, so this is circulation around any circle passing through the whole of your torus, is going to have this kind of formula for the velocity. And so one thing which is interesting to note here is that the velocity is going to depend on both your major radius and your minor radius. It's going to depend, in fact, on the shape of your torus and on your the radius of your vortex ring. So if you have a smaller r, so if you're taking a smaller scale, it's going to move faster. But there's also an influence of the ratio between the major radius and minor radius of your torus. And so, one thing about the cylindrical Euler equation is that this is in fact a Lake equation. Sorry, I'm speaking from the point of view of Lake equations, so I'm trying to bring everything to Lake equations. So if you look at the cylindrical Lake equations, in fact, it's a lake with a depth function, which is in fact exactly the distance to the boundary. So this is exactly what you have when you have a straight, when you have a beach with a constant slope and a shoreline, which is exactly a shoreline. So this is exactly the situation if you know about a little bit about Belgian geography. So this is exactly the shoreline of Belgium with a constant slope beach and a straight line for the shore, essentially. And so this is a kind of lake here. And so this gives us some insight about what would be the possible. So those vortex, those solutions, in fact, they give us, so all this theory about vortex rings for the Euler equation, this gives us some information. This gives us, in fact, some solutions and some desingularized solutions for vortices on the Lake equation. So this says that if we have, so this is kind of nice lake with a constant slope beach with, so constant slope depth with so we have a linear depth function together with a straight boundary. So if you're just working in the half space problem, then you have solutions which are moving parallel to the boundary with the velocity depending on the radius and also on the distance. So r is going to be the distance to the shoreline. And then you have this second parameter, which is going to say that when the scale of your vortex, when you're considering smaller vortex structures, you're going to move faster. So this is about the cylindrical Euler equation. And now I want to move to what I have promised to you in the title. So those are this is vortex dynamics for the Lake equations. And so a thing that has been done is that there is a formula. This formula, you can think it, just go back 2 slides. So this is essentially Kelvin and Higgs work for the velocity here. And so there is a formula for the velocity of, this is a formal formula for the velocity of a vortex in the Lake model. So this vortex is going to be, so I'm taking here the cross product between the gradient essentially of the log curve of the depth here, and then this is proportional to the vortex circulation here, and then you're taking the dot, the cross product with a vertical vector. So this means, in fact, that you're essentially rotating the gradient by 90 degrees. And then we have an additional factor, which is logarithm of 1 over epsilon. 1 over epsilon, this is the vortex, the radius of your vortex here. And so this is something that was obtained by Richardson in 2000. This is published in Journal of Fluid Mechanics. And so this is what he calls formal matched asymptotics. What does it mean, formal matched asymptotics? He's in fact writing some ansatz for the formula for a vortex solution with lots of coefficients, and then he's kind of choosing the coefficients in such a way that the first terms in the asymptotic expansions cancel, and when the first terms cancel in the asymptotic expansion, he's getting this formula. So maybe one thing to say, just to explain this, a few things to say this, is that first, this is consistent. I mean, this is exactly the same formula as the Kelvin and Higgs problem if you apply this to the particular case of cylindrical Euler equation. The other thing that this says to you is that vortices, they are expected to move at constant depth. So this movement at constant depth, this is what is expected here. And maybe I can give you two, let us say, okay, I'm going to come with a proof, or I'm going to come with a theorem at least later, before the end of the talk. But before going to the theorem, I just wanted to say one thing. First thing is that you can think that the lake is something like having a shore with some slope. This means that you're not having a sharp interface at the boundary, but you have something like a boundary which is spread out all over, and you have a kind of smoothened version of the boundary. And remember, the vortices for the Euler equation in a domain, they interact with the boundary. They move parallel to the boundary. Here you have a boundary which is somehow spread out everywhere. When your B is increasing, when B is changing value, you're in some sense getting out of your lake. When B is going up, you're going inside your lake. And so the way to move, what plays a role of the B plays, in fact, the depth function plays a role of the boundary. And so if you want to think that vortices for the Euler equation, they should move parallel to the boundary, then they should move along level sets. And so this says that the dynamics is something here which is completely local and only depends at the first order on the depth function, what is called the bathymetry. So this bathymetry justifies the B here coming from the Greek root. So this is the thing. Another way to explain this, and this is maybe closer to what we'll be doing in our proof, is that you should think that your vortex, you need to preserve several quantities, and among this you have the kinetic energy, and you also have the total vorticity, and if you change the depth, you're changing the shape of your vortex, and this is bad for conservation loads. And so the best way to stay in the lines that the conservation laws have drawn, the best way to stay in this kind of situation is to keep a constant depth. So this is the kind of way of changing the solution as less as possible to preserve its structure. And so, in fact, this is I have been aware of this paper by Richardson for some time, in fact. And at some point, for a long time, I had been wondering about what was happening I was wondering what was happening about this. There was anything in the physical literature about this kind of structure besides this paper by Richardson. And then, so before I explain to you what I have written here on the bottom of the slide. But so what happened is that 2 years ago, when we were finishing this paper, I missed a connection to fly back to Belgium in JFK, and there I had some time, and I really took seriously. I had some time in a hotel somewhere on Long Island, and I spent some time really trying to find what had been done. And so I found some. You see, found a few. You have here a few references here below. And so what they have, so there have been some interest, and the interest, and so this is the meaning of the reason of the image here is that if you look at those papers, the typical sentence that you would find in the first paragraph is to say that rip currents make more casualty than sharks every year on the beaches. So rip currents, what are they? They are vortex-like structures appearing on beaches, and when you're swimming, you have the risk of being taken far away from the beach and not being able to reach again this beach, and so you have lots of safety instructions about this, and so you had some need to explain this, and this is not only the lake equations, but what is happening. So what more or less what they're explaining in this kind of papers, in this series of papers, that they're explaining that you have some vortex pairs forming somewhere in the open ocean, then they move towards the beach, and then when they are next to the shore, then you have something that looks like the dynamics for the lake equations, and then they move at some point, which is a kind of local maximum of the depth, and they sit there, and you have some vortex-like structure that remains. So this is part of a global explanation. I have no ambition of saving anybody's life with our theorems, but this gives you some other context. One also interesting thing is that in one of the papers they find back Richardson's, I think it's a paper by Centurione, he rewrites, he reobtains the Richardson equation, but he explains this is too complicated. I'm going to work with an analogy with the dynamics for the vortex rings, and he's starting from the dynamics for the vortex rings, and by some kind of analogy, linearization, he finds back this kind of equations. So this is about what we expect. And so, what we have as rigorous results, so we first begin working on this with another PhD student here in Louvain, Sébastien de Varela, and we considered the stationary case. So the stationary case, you consider a point which is the maximum point of the depth, and then you will obtain the existence there of a family of stationary solutions of the lake equations, which will be concentrated at this point. And so there are two ways of approaching this. Justin de Keyser, he also obtained a different construction giving you based on the vorticity, which gives you such concentrating stationary solutions. So the point there is that you're having stationary solutions concentrating towards a stationary point of your lake equation. So now I come to our result. So we have, so this is the main result that we have, is an asymptotic result for the evolution of vortices. And so what we obtain, the short statement, the slogan, is that vortices, they follow level lines of the bathymetry. And so you can just look at the level lines of the bathymetry, you just buy a nice, so those are, you would find this on nautical charts that sailors use to see whether there's a risk of having some trouble with your boat, and so you have this this kind of so you're just following the level lines that you would find in the nautical chart. And so what we're assuming, we're making some assumptions, and so maybe I explained to you that there's assumption first. Maybe the vorticity is going, the vorticity is converging to a multiple of the Dirac delta. So gamma n is the integral of the vorticity, so I'm assuming this is concentrated. Then we're assuming something about the initial energy and the total circulation. We're assuming that the energy and the total circulation, this quotient, is going to infinity. And then we have some kind of regularity, so this kind of L infinity bound related to the quantities appearing here. And then what we're saying is that our solution, the vorticity of our solution, converges weakly to, at every time, to a Dirac delta. But we should rescale, make some rescaling in time. The rescaling in time is done by the energy divided by the total circulation. And if you take out this factor, you're converting to a solution of an equation which is something which is following the level lines of the bathymetry here. So maybe so we have really an assumption about the behavior of the vorticity here. We have some assumption here which says that we are in a regime. This is an assumption saying that we are in a regime in which things are concentrating, and this is. So maybe the best way to explain this is we need to put some assumption somewhere which will make that our solution is not creating lots of small vortices everywhere. So this plays a role in the concentration. I will just give you an example of initial data satisfying this kind of thing. So the vorticity, this is the curl of the n. We have a quantity which is the total circulation with the integral of omega n. And then we have the total vorticity. This is omega n of t, and this is going to be the weighted. This is the same as gamma n, except that we're putting here a weight b in the integral. And in contrast to what is happening if you're considering the other equation, when b is not a constant, this is not, omega n is not a multiple of gamma n. And then there's a quantity which is the total energy. In fact, when you're considering the total energy, you should integrate with respect to the vertical variable, and you get this additional b. We should also think this omega n is kind of integrating over the whole volume, whereas gamma n is integrating over the surface. This is, if you want to make a physical difference between those two, you will get this. And so, a special case is a case when omega n is going to be gamma n divided by epsilon n squared. So this is a rescaled profile at the point r star. Then if you consider this with a function which is c infinity with compact support integral 1, then what you will get omega n naught over gamma n at 0. This is going to go to delta. So sorry, there's R naught and R star are the same here, and I think there's X star. All of these are supposed to be the same. If you look at omega n 0, so this is going to behave like gamma n over epsilon n squared, and this is going to be exactly the same as what you have here, because when you're looking at your energy, I should have begun first by the energy. If you compute the energy of this kind of solution, so you're having a vorticity, you have to compute the associated function out of this, and you get something which is divergent with the scale epsilon n. And so what you get is that omega n rescaled by this factor is going to Dirac delta at every s, and with s obeying this equation. And so if you look at this factor, you could, of course, here, if you are, the problem here, maybe to explain things, is that here I have, in fact, gamma n can vary, or I can put, maybe, if you put yourself in a regime where gamma n times logarithm of 1 over epsilon n is converging to something, then you can take this out and write some kind of limit. Otherwise, you have some factor, and if you think with gamma, say, which is fixed, then you have accelerating time scales appearing here, and so. But you're getting, in fact, you're getting, in fact, you have this gamma over 4 pi logarithm gradient of b. You're getting the same kind of equation here. you have here an additional b coming here, which is compensating the fact that you have the logarithm in Richardson. So another thing I wanted to mention is that, in fact, an interesting feature of this statement of the theorem is that it gives you, if you want to take out the scaling, you can rescale, make a change of variable to make this rescaling in the time variable disappear. And this is going to say you that the localized vortex of energy circulation gamma and position will have a velocity which is given by this formula. So for simple profiles, this is exactly equivalent to Richardson's law. The only real difference that we have here, and I think this is, at least I have found this quite interesting, is that we do not have anymore a characteristic scale appearing here. So we're saying that it's moving according to a velocity. It's not depending on the radius of the vortex. It's depending on the energy of the vortex and the circulation of the vortex. And this is what is really playing a role here. Or the other advantage is that you're losing the factor 4 pi, but this is just a technical feature of using energy and circulation here. So I have just a few minutes to just give you, to explain to you maybe what the proof is about. So maybe the proof...
Excuse me, just quick question. So you always consider here just one vertex, right? No interaction.
Just one vertex.
Just one single vertex. Okay, yeah, thank you.
This is an open problem, I would say. So if you want to think about this, just about this equation, what I would think is that there should be something like a localized, say a kind of semi-local version of the energies should play the same role. In fact, maybe about several vortices, it shouldn't be a problem, except that you cannot do it in the proof. So if you look at the intuition, this is a completely local dynamic. These are completely local dynamics. It shouldn't play any role, but we don't know. So the crucial thing is that you have transport of the potential vorticity, and so you can look about how this potential vorticity is going to behave. And you have conservation of several quantities, energy and circulation. And then you have this total vorticity. This total vorticity, this is bad news. It is not conserved. But the good news is that it's almost conserved. So we can write something which is an asymptotic conservation, because in origin, this thing is going to be much smaller than omega n. And so this gamma n squared, this is in fact much smaller than the energy, and this is going to disappear asymptotically. And so we can do as if, in our proof, we can do as if this quantity was preserved. And then we have something about concentration estimates. So this is one thing I wanted to show you. We don't have any characteristic radius in our proof. The role of the characteristic radius, we define it, it's in fact as some combination. So there's a formula, the logarithm of this characteristic radius is related to the energy, total vorticity, and total circulation. And this is what we take as a definition of our characteristic radius, and we can get that the solution does not, because of all our assumptions, the solution does not concentrate outside, concentrates inside sets of this kind of radius. Here, and maybe the last thing to explain is that the main issue, so maybe I didn't say, I should have been more honest at the very beginning, but we have a restriction on B, which is quite stringent, is that B should be bounded away from zero, should be bounded and bounded away from zero, which is, for a lake physically, is not what you would expect. You would expect the depth to go to zero. And a lot of what we're doing is trying to write some behavior of the green function of the elliptic problem. And it is writing this green function of this elliptic problem with a B. And here, this is a typical formula we're using, is that we're rewriting things. We're saying that the green function of this problem, you can write it more or less as square root of B times the green function of the classical Dirichlet problem. But this is, so this is something and we need this to be robust enough so that we can go through the proof. So maybe I just have 1 minute to explain what we have done. So what we have done is that we're assuming, in fact, that B is supposed to be constant on the boundary. And I'm just, okay, the last time I'm going through, maybe one thing to say is that the interesting about having B constant next to the boundary is that this prevents, in your Hamiltonian system, this prevents your vortex colliding with the boundary. Of course, this makes things simpler at the level of the Hamiltonian system. This does not mean that it should be possible to say that at least from up to the collision time with the boundary, you should be obeying the same thing. Second question would be having B vanishing on the boundary. Another question, maybe dual to the second one, would be what is happening when omega is unbounded and so B is unbounded? You expect a decent, complete theory of this thing to cover the complete case of the cylindrical Euler equation. For instance, for the moment, we can just get some subdomain. And then the last question, raising the question I had just a few minutes ago, would be what is happening with multiple vortices. So first, what is happening with multiple vortices for small timescales, and then being much more ambitious would be to understand what is happening when you have two vortices. So you could imagine just B being a radial function, and you put two vortices on the same circle, on the same level line. So they're going to start with the same strength. So they're going to move at constant velocity on your circle, and then at some point they will collide. They will not collide, they will form a vortex pair, but then at which distance are they going to form a vortex pair? How is this transition happening? There should be definitely some interesting structure appearing there. So thank you very much for your attention. I would be happy to have some questions.